Welcome to this comprehensive guide on well drilling operations. Over the next hour, we will walk through every phase of drilling an oil or gas well, from initial site preparation to the moment hydrocarbons reach the surface. This is a technical process that combines geology, engineering, and careful execution, and we will explain each step in detail so you understand exactly how it works. Before any drilling begins, extensive geological work has already been completed. Geologists use seismic surveys to map underground rock formations. Seismic waves are sent into the ground, and the reflections reveal the structure of rock layers thousands of feet below. Computer models analyze this data to identify potential hydrocarbon reservoirs. For our example, the target reservoir is at 12,000 feet depth, which is fairly typical for many oil and gas wells. The geological team has determined that this location has the right combination of source rock, reservoir rock with adequate porosity and permeability, and a trap structure that would contain commercial quantities of hydrocarbons. Once a location is selected and permits are obtained, site preparation begins. The drill site, called a pad, must be cleared and leveled. This pad is typically 3 to 5 acres and needs to support extremely heavy equipment. The ground is graded flat and covered with compacted gravel or crushed rock to create a stable foundation. Engineers calculate the load-bearing requirements because some equipment can exert over 50,000 pounds per square foot of pressure on specific points. Poor foundation work can lead to equipment failure or dangerous rig instability. Workers excavate a cellar, which is a rectangular pit approximately 10 feet deep and 10 by 10 feet in dimensions. The cellar serves two purposes. It provides workspace below ground level for installing wellhead equipment, and it houses the blowout preventer stack. The cellar is typically lined with steel or concrete to prevent collapse. Nearby, crews install utility systems including electrical power, water supply, and fuel storage for the diesel generators that will power the rig. The drilling rig itself arrives disassembled on multiple trucks. A modern land rig suitable for drilling to 12,000 feet consists of several major systems, each serving a critical function. The power system typically consists of multiple diesel generators producing 2,000 to 3,000 horsepower, which supply electricity to all rig equipment. The hoisting system includes the derrick, a tall steel tower usually 130 to 150 feet high. The drawworks, which is essentially a powerful winch system with a large spool that can raise and lower pipe with precise control. The crown block at the top of the derrick, and the traveling block that moves up and down. The rotating system consists of the rotary table, a circular opening in the rig floor that can rotate to turn the drill string, or alternatively a top drive system. The circulating system includes large reciprocating mud pumps that can move drilling fluid at high pressures and flow rates, along with mud tanks, shale shakers, and related solid control equipment. The well control system centers on the blowout preventer stack with its ramps and annular preventers. Supporting all of these is the substructure, the steel framework that elevates the rig floor 20 to 40 feet above ground, providing clearance for the blowout preventer and wellhead equipment. Assembly takes several days. Cranes position the substructure over the cellar, then the rig floor is mounted on top. The derrick is raised into vertical position, either by telescoping if it's a mobile rig or by lifting pre-assembled sections with cranes. At the top of the derrick is the crown block, a stationary set of pulleys. The traveling block is a mobile set of pulleys that hangs from the crown block on steel cable called drilling line. This block and tackle system provides mechanical advantage, allowing the drawworks to lift loads weighing hundreds of thousands of pounds. The drill pipe is stored on racks adjacent to the rig floor. The blowout preventer, commonly called the BOP, is perhaps the most critical safety device. This stack of heavy steel valves is installed on the top of the wellbore. A typical BOP stack for land drilling includes several components stacked vertically. At the bottom are pipe ramps, which are hydraulically operated steel blocks that can close around drill pipe of specific sizes. Above those are blind ramps or blind shear ramps, which can close completely and even cut through the drill pipe in an emergency. At the top is an annular preventer, which uses a reinforced rubber donut that can squeeze closed around any size pipe or close completely on an open hole. The entire BOP stack may weigh 300,000 pounds and stand over 30 feet tall. All ramps are operated by high-pressure hydraulic systems with redundant controls so they can close in few seconds if formation pressure threatens to cause a blowout. The mud system is extensive. Drilling mud is a specially engineered drilling fluid that performs multiple critical functions. It cools and lubricates the drill bit, which can reach temperatures over 400 degrees Fahrenheit from friction and bottom hole temperature. It carries rock cuttings up from the bottom of the hole to the surface. It exerts hydrostatic pressure on the formation to prevent formation fluids from flowing into the wellbore. It forms a thin filter cake on the wellbore wall that prevents fluid loss and stabilizes the hole. The mud can be water-based using fresh water or brine as the base, or oil-based using diesel or mineral oil. Additives control its properties. Barite is added to increase density and hydrostatic pressure. Bentonite clay increases viscosity. Polymers control fluid loss. And various chemicals adjust pH, prevent corrosion, and stabilize shale formations. The mud is stored in large steel tanks. Each can hold from 100 up to 1,000 barrels. A typical system has 2,000 to 5,000 barrels of mud in circulation. Mud is pumped from the tanks through a standpipe up the side of the derrick, then through a flexible high-pressure hose called the rotary hose or Kelly hose, then down through the swivel at the top of the drill string. The mud flows down the inside of the drill pipe, through the drill coolers, and exits through nozzles in the drill bit. It then flows back up the annular space between the drill pipe and the wellbore wall, carrying rock cuttings with it. At the surface, the mud exits through the bell nipple and flows across shale shakers, which are vibrating screens that separate the cuttings. The cleaned mud flows back into the tanks for recirculation. A complete cycle takes several minutes depending on well depth, where it may even reach few hours. A mud engineer is on site continuously monitoring and adjusting mud properties. Key properties measured include density or mud weight, measured in pounds per gallon or ppg, viscosity, which affects how well it carries cuttings, gel strength, which is how much the mud solidifies when circulation stops, fluid loss, which indicates how much liquid will escape into permeable formations, and pH, which affects corrosion rates and chemical stability. The mud engineer uses laboratory equipment in a mobile unit to test these properties every few hours and adds materials as needed to keep everything within specification. With the rig assembled and systems tested, drilling can begin. The driller operates the rig from a control console that may have 50 or more gauge switches and computer displays. Key parameters monitored include weight on bit, which is how much downward force is applied to the drill bit, typically 10,000 to 50,000 pounds. Rotary speed, measured in revolutions per minute or RPM, typically 60 to 120 RPM for the rotary table or 100 to 200 RPM for top drive. Torque, which indicates how much resistance the bit encounters. Pump pressure, typically 2000 to 5000 psi at the pumps, and rate of penetration or ROP, which shows how fast the bit is drilling, typically 30 to 200 feet per hour depending on the formation. Wells in the oil and gas industry come in several types based on their purpose. The first type is exploration wells, drilled to confirm the presence of hydrocarbons in a reservoir before full development. After successful exploration, appraisal wells are drilled to evaluate reservoir size, productivity, and economic viability. Once the field is confirmed, development wells are drilled. They can be production wells to extract hydrocarbons, or injection wells to support reservoir pressure through water or gas injection. Wells can also be categorized by trajectory. Vertical wells are the simplest and drilled straight down, while directional and horizontal wells are angled or drilled laterally through the reservoir. One of the biggest applications of directional and horizontal wells is multilateral and extended reach wells, which incorporate multiple branches or long horizontal sections from a single surface location to reduce cost and environmental footprint. Now let's explore the detailed steps and procedures involved in drilling a well. A well isn't just one single hole or section. The well is drilled in multiple sections, and each one becomes smaller as you go deeper. The first section drilled is the conductor hole, typically 36 inches in diameter and 40 to 100 feet deep. A large tricone roller bit is used, which has 3 rotating cones with steel or tungsten carbide teeth or inserts. The bit is screwed onto a bit sub, then heavy drill coolers are added above it. Drill coolers are extra thick, heavy pipe sections, typically 6 to 9 inches in outer diameter with a 2 to 3 inch bore. Their weight provides the downward force on the bit. Above the drill collars, regular drill pipe is added with optional heavyweight drill pipe in between as a transition zone. Drill pipe is typically 30 feet long with threaded tool joints at each end and has an outer diameter of 5 inches and wall thickness of about half an inch. The killie, a 40-foot section of square or hexagonal pipe, is connected to the top of the drill string. The killie passes through the rotary table, which grips it with a killie pushing. When the rotary table turns, the killie turns, rotating the entire drill string and bit. As drilling progresses and the killie is drilled down close to the rig floor, the crew must add another joint of drill pipe. This process is called making a connection. The driller stops rotation and sets slip switch-shaped gripping devices in the rotary table to hold the drill string. The killie is disconnected using large pipe wrenches called tongs. A new joint of pipe is lifted from the rack with a traveling plug, stabbed into the top of the drill string, and screwed in with the tongs, applying thousands of foot-pounds of torque. The killie is then reconnected on top, and drilling continues. This happens every 30 feet, roughly every 15 to 30 minutes during active drilling. Many modern rigs use a top drive instead of a killie and rotary table system. A top drive is a large motor suspended from the traveling block that grips the top of the drill pipe directly and rotates it. This system allows crews to add pipe in stands of 2 or 3 joints at once, reducing connection time. It also provides better weight control and the ability to rotate while tripping pipe in or out of the hole. After drilling the conductor hole to depth, typically 40 to 80 feet, the bit and drill string are pulled out of the hole in a process called tripping out. The driller raises the traveling plug, lifting the drill string. When a tool joint appears above the rig floor, slips are set. The connection is broken with tongs, and the joint is lifted clear and dragged vertically. This continues, removing pipe one joint or one stand at a time until the entire drill string is out. This can take several hours for a deep well. The conductor casing is then run into the hole. Conductor casing is large diameter pipe, 30 to 36 inches with relatively thin walls. It may also be 20 to 26 inches. Joints of conductor casing are lifted with the traveling plug, stabbed together, and either threaded or welded. Once the string is assembled and lowered into the hole, cement is pumped down the inside of the casing and pack up the annulus between the casing and the wellbore. A plug is placed inside the casing to separate the cement from the drilling mud, and then drilling mud is pumped behind it to displace the cement. Enough cement is pumped to fill the annulus from bottom to surface. The cement serves multiple purposes. It holds the casing in place, seals the annulus, protects the casing from corrosion, and prevents flow migration between different formations. Cementing is a specialized operation performed by a service company. A cementing unit, essentially a high-pressure pump truck, mixes dry cement with water and additives on the fly and pumps it at high rates and pressures. The cement is typically Class G or H oil well cement, with accelerators to make it sit faster, retarders if pumping time needs to be extended, dispersants to keep it flowable, and weight materials to match formation pressure. After pumping is complete, the cement must cure, typically requiring 8 to 24 hours to develop sufficient strength. A cement bond log, a specialized downhole tool, may be run to verify that the cement fills the annulus completely with no voids or channels. An alternative method for installing conductor casing is to drive it into the ground using a hydraulic or pneumatic hammer, eliminating the need to drill a conductor hole first. This method is commonly used in areas with relatively soft, unconsolidated near-surface formations such as clay, sand, or loose sediments. A large pile driving hammer is mounted on top of the conductor pipe, and the pipe is driven downward by repeated impact blows. The conductor is driven to refusal, which is the point where the soil becomes too hard or compact for further penetration, or until the required depth is reached. Driving to refusal typically occurs at 30 to 100 feet depth depending on soil conditions. This method is faster and less expensive than drilling because it eliminates the need to mobilize drilling equipment for the shallow conductor section, and no drilling mud or cuttings disposal is required for this phase. However, it is only feasible in suitable geological conditions and cannot be used in areas with hard rock, boulders, or cemented formations near the surface. After driving the conductor to refusal, the top is cut to the proper height, and cement may still be pumped inside and around the conductor to provide additional support and seal, though some operations rely only on the mechanical grip of the surrounding soil. Once the conductor casing is cemented, the next section begins. A smaller bit is run through the conductor casing to drill the surface hole, typically 17.5 inches in diameter, to a depth of 1,000 to 3,000 feet. This section penetrates shallow rock formations and must be drilled with careful control to avoid damaging freshwater aquifers. Formation samples are collected continuously. A mud logger monitors the cuttings, examining them under microscopes and ultraviolet lights to detect any traces of hydrocarbons. Cuttings are described in terms of lithology, noting whether they are sandstone, shale, limestone, or other rock types, along with their color, hardness, and grain size. This information is recorded on a mud log, which is a continuous graphical record of the well paired with drilling parameters. Drilling continues until the planned depth for the surface casing is reached. The drill string is stripped out, and the surface casing is run and cemented. Surface casing is typically 13 3/8 inches in diameter, with walls of 0.48 to 0.72 inches thick, depending on the pressure rating needed. This casing string is critical because it isolates and protects all freshwater zones and provides structural support for the well. The cement job must be excellent, with cement circulated all the way to the surface. After cementing, the diverter is removed and the BOB stack is installed on top of the surface casing. The BOB is bolted to the casing head, which is a heavy flanged fitting on the top of the surface casing. All BOB functions are tested at maximum rated pressure, typically 3,000 to 15,000 psi, depending on the expected formation pressures. This ensures it will function perfectly in an emergency. The diverter is used to mainly divert shallow gases away from the rig site, while BOB's main function is to shut in the well against high pressures. That is why the BOB pressure test is mandatory. The next section is the intermediate hole, drilled with a 12.25-inch bit to a depth that depends on the geology, but typically 6,000 to 9,000 feet. This section transitions from shallower, lower pressure formations into deeper, higher pressure zones. The drilling fluid weight may be increased from 9 or 10 ppg to 12 or 14 ppg to maintain pressure control. As depth increases, formation pressure increases due to the weight of overlying rock. The mud weight must be high enough to exceed the pore pressure in the formations being drilled to prevent an influx of formation fluids, but not so high that it fractures the weaker formations higher up in the hole. This balance is called the drilling window, and it becomes narrower as you drill deeper. During this intermediate section, drilling becomes more complex. The bit is rotating at the bottom of a hole that is now thousands of feet deep. The drill string itself weighs hundreds of thousands of pounds and can experience vibration and buckling. The driller must carefully manage weight on bit and RPM to avoid damaging the drill string or bit. Downhole motors may be used, which are positive displacement motors powered by mud flow that rotate the bit independently of the drill string. These motors allow faster penetration rates and directional control. Many wells today are not drilled vertically, but are intentionally deviated to reach targets that are horizontally offset from the surface location, or to drill through a reservoir horizontally to maximize contact with a productive formation. Directional drilling requires specialized equipment and expertise. A mud motor with a bent sub is used to change the direction of the hole. The bent sub creates a slight angle, typically 1 to 3 degrees, between the motor and the bit. When the drill string is not rotating and only the mud motor is turning the bit, the well will curve in the direction the bent sub is pointing. This mode is called the sliding mode, and it is used for building an angle in a specific direction. When the entire drill string is rotated from the surface, the bent sub effect averages out and the well drills relatively straight. This is what is called the rotating mode. By alternating between these two modes, the directional driller can steer the well along a planned path. Measurement while drilling tools, called MWD, are incorporated into the drill string near the bit. These tools contain sensors that measure inclination angle from vertical, azimuth or compass direction, and tool face orientation. They also measure downhole drilling parameters like temperature, pressure, torque, vibration, and weight on bit. This data is transmitted to the surface in real time using mud pulse telemetry. The MWD tool has a valve that creates pressure pulses in the mud column by restricting flow momentarily. These pulses travel up the mud column at the speed of sound in the fluid, about 4,000 to 5,000 feet per second, and are detected by pressure transducers at the surface. The pulses are decoded to recover the downhole data. Data transmission rates are slow, typically 1 to 12 bits per second, but adequate for real-time directional control. Logging while drilling tools, called LWD, add formation evaluation capability. These tools measure properties of the rock formations being drilled. A gamma-ray sensor measures natural radioactivity, which helps identify shale versus sandstone or limestone. Resistivity sensors measure the electrical resistance of the formation, which indicates whether pores are filled with conductive salt water or resistive hydrocarbons. Density and neutron sensors measure porosity, the percentage of void space in the rock. Sonic sensors measure compressional and shear wave velocities, which indicate rock mechanical properties. All this data is recorded downhole in memory and also transmitted to the surface in real time. As the intermediate hole is drilled, the geological team continuously analyzes the data. The actual formations encountered are compared to the pre-drilled geological model. Sometimes surprises occur, such as unexpected pressures, low circulation zones where mud flows into highly fractured rock, or shows of hydrocarbons in formations not predicted to be productive. The drilling team must adjust the plan accordingly. If unexpected high pressure is encountered, mud weight must be increased. If the mud weight required to control pressure would fracture the formations at the previous casing show, then an additional casing string must be set earlier than planned. When the intermediate section reaches its planned depth, the drill string is stripped out and the intermediate casing is run. This casing is typically 9 5/8 inches in diameter. The casing string may be several thousand feet long and weighs several 100,000 pounds. Each joint of casing is lifted with a traveling block stabbed into the joint below and made up with the hydraulic casing tongues that apply precise torque. Casing connections must be perfectly clean and properly torqued because they must seal against high pressures. The casing string may and may not be run with centralizers, which are spring-loaded devices that keep the casing centered in the hole. Centralizers ensure good cement distribution around the entire circumference of the casing. A casing float shoe is installed on the bottom of the casing string. This is a short section with a check valve that allows fluid to flow down but not up. Above it is a float cooler, another check valve 1 or 2 joints up from the bottom. These components are called the show track and they serve several purposes. They allow the casing to be filled with mud as it's lowered, reducing the load on the rig, but prevent backflow. They prevent cement from flowing back into the casing after pumping. They provide a landing surface for cementing plugs. Once the intermediate casing is cemented and tested, drilling continues with a smaller pit through the intermediate casing. The production hole, typically 8.5 inches in diameter, is drilled from the intermediate casing show down to the target reservoir. This is the most critical section because it will penetrate the productive formation. The mud system must be carefully managed to avoid damaging the reservoir. If mud weight is too high, it can force drilling fluids into the porous reservoir rock, reducing permeability in a zone around the wellbore called the invaded zone. This is known as formation damage and can significantly reduce well productivity. Oil-based mud is often used for drilling the reservoir section because it causes less damage to oil-bearing formations than water-based mud. The rate of penetration typically decreases as depth increases because the rock becomes harder and more compacted. In shallow soft formations, 100 to 200 feet per hour may be achieved. In deep hard formations like granite or chert, the rate may drop to 20 or even 10 feet per hour. The drill bit must be matched to the formation. Tricone roller bits work well in soft to medium formations. For hard formations, polycrystalline diamond compact bits called PDC bits are often superior. PDC bits have fixed cutters made of synthetic diamond bonded to tungsten carbide studs. They have no moving parts and can drill faster in hard rock if operated at the correct parameters. However, they are more expensive and can be damaged if used improperly. A tricone bit might cost $5,000 to $10,000, while a PDC bit can cost $20,000 to $50,000 or even more. Bit selection and drilling optimization are critical for cost control. Drilling costs can range from $50,000 to over $1 million per day depending on the rig size, water depth for offshore wells, and location. Every day saved is significant money. Drilling engineers use software that analyzes drilling data in real time to optimize parameters. The goal is to maximize rate of penetration while minimizing bit wear and avoiding drilling problems. The dull bit is examined when tripped out to understand what happened downhole. Bits are graded using a standardized system that describes wear on the cutting structure, bearings, and gauge. As the production section is drilled, geological monitoring becomes intensive. The mud logger examines cuttings continuously and monitors gas detectors. Gas detector instruments continuously sample the mud returning from the well and measure concentrations of methane, ethane, propane, butanes, and pentanes. An increasing gas indicates that the bit is drilling through a formation containing hydrocarbons. The mud may also show fluorescence under UV light if oil is present. These shows are carefully documented because they indicate potential productive zones. During the drilling stage, multiple problems frequently occur that require immediate recognition and response. Even with careful planning, advanced technology, and experienced crews, the subsurface environment presents numerous challenges that can halt operations, damage equipment, or create dangerous situations. Understanding these drilling problems, their causes, warning signs, and solutions is essential for safe and efficient operations. Let's examine the most common and significant drilling problems encountered in well operations. The first major category of drilling problems involves lost circulation, which occurs when drilling fluid flows into the formation instead of returning to the surface. This is one of the most common and costly problems in drilling operations. Lost circulation happens naturally when the wellbore intersects natural fractures, cavernous formations, or highly permeable zones that can accept fluid faster than it can be circulated. It happens accidentally when the mud weight or the equivalent circulating density, known as ECD, approaches the fracture gradient, causing the creation of microfractures. The severity ranges from partial losses, where some mud returns but at a reduced rate, to total losses, where no mud returns at all. Warning signs include a decreasing mud level in the tanks, reduced mud return rates measured at the flow line, and decreased pump pressure. Both the driller and the mud logger monitor the active tank system, and any unexplained loss of several barrels indicates lost circulation. Lost circulation creates several serious problems. Without adequate mud returns, rock cuttings cannot be removed from the wellbore, leading to bit bowling where cuttings pack around the bit, or hole packing where cuttings accumulate in the annulus, causing string to be stuck. The hydrostatic pressure from the mud column decreases when fluid level drops in the wellbore, potentially allowing formation fluids to flow into the well and creating a kick situation. Additionally, lost circulation materials and remediation procedures are expensive and time-consuming. Solutions depend on the severity of the losses. For minor losses, lost circulation material, abbreviated LCM, is added to the mud. LCM includes fibrous materials like shredded cellulose or mineral fiber, granular materials like ground walnut shells or calcium carbonate, and flaky materials like mica or cellophane flakes. These materials spread across fractures and pores, forming a seal that stops or reduces fluid loss. For moderate losses, specialized pills are prepared. A pill is a slug of specially formulated fluid, typically 10 to 50 barrels, pumped into the well to address a specific problem. Lost circulation pills might contain high concentrations of LCM, gunk squeeze materials that are two-component systems forming a gel when mixed downhole, or settable materials like pentonite diesel oil mixtures. The pill is spotted across the loss zone by pumping it down the drill string and out of the bit, then pulling the drill string up so the pill sits opposite to the thief zone. For severe total losses, cement plugs may be required. A balanced cement plug places cement across the loss zone with equal hydrostatic pressure inside and outside the drill string to prevent the cement from being pushed entirely into the formation. After the cement hardens, drilling resumes through it. In extreme cases, casing must be set above the loss zone to isolate it before drilling can continue deeper. The second major problem category is stuck pipe, which occurs when the drill string cannot be moved up, down, or rotated. Stuck pipe is extremely serious because it can result in losing part or all of the drill string in the hole, requiring expensive fishing operations or even sidetracking to drill around the stuck pipe. There are several mechanisms that cause stuck pipe. Differential sticking occurs when the drill pipe is pressed against the wellbore wall by differential pressure between the mud column and the formation. This typically happens when drilling through permeable formations with high mud weight. The drilling mud forms a filter cake on the wellbore wall, and the drill pipe can become embedded in this cake. The differential pressure, often thousands of psi, creates enormous force holding the pipe against the wall. On the other hand, mechanical sticking occurs when physical obstructions in the wellbore prevent the drill string from moving freely. One common cause is poor hole cleaning, where cuttings or cavings accumulate and form a bridge above the drill string, blocking movement. In unstable shale formations, swelling, fracturing, or sloughing can collapse portions of the wellbore, physically trapping the pipe. Mechanical sticking can also result from pack-off, where cuttings tightly compact around components, especially drill coolers, in highly deviated or restricted sections of the hole. Another contributing factor is an under-gauge hole, where formations squeeze or swell, reducing the wellbore diameter smaller than the original bit size and trapping larger components such as stabilizers or coolers. Early warning signs of potential mechanical sticking include increasing drag when pulling the string, rising torque while rotating, fluctuating pump pressures, and abnormal overpull required to free pipe that previously moved smoothly. Prevention is far better than cure for stuck pipe. Proper hole cleaning through adequate flow rates and pipe rotation keeps cuttings suspended and moving upward. Minimizing the time the drill string remains stationary reduces the opportunity for differential sticking or settling cuttings to pack around it. Using low fluid loss muds minimizes filter cake thickness. Maintaining proper mud properties, including appropriate density, viscosity, and chemical treatment, helps prevent shale instability. If pipe does become stuck, immediate action is required. For differential sticking, the first response is to reduce the differential pressure by lowering mud weight if possible, or to spot a spotting fluid, which is a low-viscosity oil-based or surfactant-treated fluid pumped around the stuck section to break the filter cake seal and lubricate the contact area. For stuck pipe, the correct first action is to start working the string and jarring in a direction opposite to the direction of the string movement before stuck happens. If failed, then working the pipe by applying alternating upward and downward forces while rotating and sometimes free it. Rotation is only applied due to working the string down to prevent twist-off while working the string up. Jarring involves using specialized downhole tools called jars that deliver sharp upward or downward impacts measured in tens of thousands of pounds of force to shock the pipe free. The drill string is stretched by pulling above the jar, then the jar releases suddenly, converting the stored elastic energy into kinetic energy and impact force. If these measures fail, the pipe may need to be packed off, which means unscrewing the drill string at a connection above the stuck point using a specialized tool. If failed, special tools can be used for severing the drill string. The free portion of the drill string is recovered, and fishing tools are then used to engage and retrieve the stuck section. In the worst cases, the stuck pipe must be abandoned and the well is sidetracked, meaning a new hole is drilled around the fish by kicking off at an angle above the stuck point. The third critical problem is kicks and blowouts. A kick occurs when formation fluids, oil, gas, or water, enter the wellbore because formation pressure exceeds the hydrostatic pressure of the drilling fluid. Kicks are dangerous because they can escalate into blowouts, which are uncontrolled flows of formation fluids to the surface. Blowouts can result in fires, explosions, environmental damage, loss of life, and destruction of the rig. Primary well control relies on maintaining proper mud weight so that the hydrostatic pressure always exceeds formation pressure. Secondary well control uses the blowout preventer to shut in the well if a kick occurs. Warning signs of a kick include a pit gain, where mud volume in the tanks increases because formation fluid is displacing mud. Flow rate increases where more mud returns than is being pumped. Pump pressure decreases, indicating reduced resistance to flow. Drilling break, where penetration rate suddenly increases, suggesting entry into an overpressured zone. Connection gas, where gas appears in the mud when circulation resumes after making a connection. And changes in mud properties, such as decreased density or increased chloride content from salt water influx. When a kick is detected, the first action is to shut in the well immediately using the BOP. The well is considered shut in when BOP ramps or the annular preventer are closed and valves are open to allow pressure monitoring. There are two pressures to monitor: drill pipe pressure, which is pressure inside the drill string, and casing pressure, which is pressure in the annulus. The driller records these shut-in pressures, the pit gain volume, and the last recorded mud weight. This information is used to calculate the influx density and formation pressure. The kick must then be circulated out using a well-controlled procedure. The most common method is the driller's method, a two-circulation procedure. In the first circulation, the original drilling mud is circulated down the drill pipe and the kick fluids are circulated up the annulus and out through the choke, a variable orifice valve that controls back pressure on the well. The choke is adjusted to maintain constant drill pipe pressure, which keeps bottom hole pressure constant and above formation pressure, preventing further influx. In the second circulation, kill mud with increased density is circulated to increase hydrostatic pressure above formation pressure. An alternative is the wait and wait method, which requires only one circulation. While waiting for kill mud to be prepared, the well remains shut in with pressures monitored to detect any leaks or continuing influx. Once kill mud is ready, it is circulated through the well with the choke adjusted to gradually reduce surface pressures to zero as the heavier mud fills the wellbore. Both methods require careful execution and constant monitoring. If handled incorrectly, the kick can escalate. Underground blowouts occur when formation fluids flow from one formation into another through the wellbore, potentially creating surface eruptions at offset locations. Gas kicks are particularly dangerous because gas expands as it rises, and it can migrate upward even when the well is shut in, continuously increasing all pressures in the well. The fourth problem category involves wellbore instability and hole problems. Sloughing shale occurs when reactive shale formations interact with water-based drilling fluid, causing the shale to hydrate, swell, fracture, and cave into the wellbore. This creates an oversized, irregular hole with piles of cavings that can stick the pipe or prevent proper cementing. Plastic or mobile formations, like salt, can squeeze or flow into the wellbore under the overburden pressure, reducing hole diameter and creating undergauge sections. Fractured formations may cause lost circulation or may be so weak that they collapse into the wellbore. Prevention involves using appropriate mud systems, such as oil-based mud or specially inhabited water-based mud for reactive shales, maintaining proper mud weight to support the wellbore, but not so high that it fractures formations, and drilling through problem zones quickly to minimize exposure time. Wellbore breathing is a phenomenon where the wellbore diameter expands and contracts in response to pressure changes during connections or traps. This can indicate weak formations at the verge of fracturing or collapsing. Tight hole conditions, where excessive drag and torque indicate the wellbore is closing in on the drill string, require immediate action such as reaming, which involves working the bit up and down over a section while circulating and rotating to restore the hole to proper diameter. If tight hole persists, casing may need to be set earlier than planned to stabilize the wellbore before it becomes impossible to run casing to the planned depth. The fifth problem area is drill string failures and equipment problems. Twist-offs occur when the drill string fails in torsion due to excessive torque combined with tensile stress, typically at a worn tool joint or in the transition zone between drill pipe and drill coolers. Washouts develop when erosion from high-velocity fluid flow or vibration wears a hole through the wall of drill pipe or a tool joint. A washout is detected by decreased pump pressure and reduced return flow rate, as some mud is exiting through the hole in the string instead of going through the bit. Downhole motor failures stop rotation at the bit, while the surface equipment appears to be functioning normally, indicated by loss of penetration rate and changes in pressure and torque readings. Bit failures in drilling operations typically arise from wear, damage, or improper operating parameters, and they affect both roller cone and PDC bits in distinct but predictable ways. For roller cone bits, common failures include bearing wear, cone cracking, lost cones, and broken or worn teeth caused by excessive weight on bit, high vibration, or abrasive formations. PDC bits, on the other hand, often experience cutter wear, cutter breakage, delamination, and thermal degradation when drilling hard or interbedded formations or when cooling is inadequate. Both bit types can suffer from bit bowling, where sticky formations such as clay accumulate on the cutting structure, reducing efficiency and causing torque fluctuations. Impact damage from drilling through formations like chert or junk in the hole can also damage cutters on PDC bits or break teeth on roller cones. Symptoms of impending bit failure generally include a drop in rate of penetration, rising torque, changes in vibration levels, erratic standby pressure, and inconsistent weight on bit response. Proper bit selection, real-time drilling optimization, and maintaining correct mud properties are essential to minimize these failures and extend bit life. The sixth category encompasses drilling dysfunctions caused by vibration.
Drill string vibration reduces penetration rates, accelerates equipment wear, and causes premature failures. There are three types of vibration. Axial vibration, or bit bounce, is vertical oscillation where the bit alternately drills and lifts off bottom. This occurs when drilling hard interbedded formations where penetration rate varies. Lateral vibration, or whirl, occurs when the bottom hole assembly bends and the drill coolers contact the wellbore wall, causing the assembly to rotate around the hole eccentrically rather than about its own axis. Torsional vibration, or stick slip, is particularly damaging. The bit periodically stops rotating or slows dramatically while the drill string above continues to turn, storing torsional energy. When the bit breaks free, it accelerates to several times the average rotational speed. This cycle repeats many times per minute, creating extreme stress reversals that cause fatigue failures.
Mitigation of vibration involves selecting bottom hole assembly designs with proper placement of stabilizers to control bending, operating at drilling parameters outside the vibration zones, using shock subs that incorporate damping elements, and utilizing advanced drill bits designed to operate smoothly in specific formations. Modern rigs with high-frequency data acquisition can detect vibration patterns in real time and alert the driller to adjust parameters before damage occurs. The driller changes weight on bit, rotary speed, or flow rate to find a combination that drills smoothly. The seventh problem is hydrogen sulfide, often abbreviated H2S, which is a highly toxic and corrosive gas sometimes encountered when drilling through formations containing sour oil or gas. H2S is colorless with characteristic rotten egg odor at low concentrations, but at high concentrations it paralyzes the olfactory nerve so it cannot be smelled, creating a false sense of safety. Concentrations above 100 parts per million or ppm are immediately life-threatening, and exposures above 500 ppm cause rapid unconsciousness and death within minutes. H2S is heavier than air and accumulates in low areas. It is also flammable and forms explosive mixtures with air. When H2S is expected, extensive safety procedures are implemented. All personnel receive H2S safety training and carry portable sensors that alarm if H2S is detected. Breathing air systems or self-contained breathing apparatus are positioned around the rig. Wind direction indicators help plan escape routes upwind from potential releases. The rig is equipped with automated gas detectors that trigger alarms and shut down ignition sources. When drilling through H2S bearing formations, the drilling fluid is treated with scavengers, chemicals that react with and neutralize H2S, such as zinc oxide, zinc carbonate, or various organic compounds. Specialized metallurgy is required for drill string, casing, and wellhead components because H2S causes sulfide stress cracking, a form of embrittlement that can cause sudden failure of high-strength steels. Sour service-rated materials with restricted hardness and specified compositions must be used in H2S environments. The eighth challenge is high-pressure, high-temperature wells, abbreviated HPHT, which present multiple difficulties. High pressure requires heavier mud weights, often 17 to 20 ppg or higher, which reduces the drilling window and makes it difficult to avoid both lost circulation and kicks. High temperature, defined as bottom hole temperatures above 300 degrees Fahrenheit, has many effects, where it causes degradation of mud properties and thermal expansion of fluids, which affects pressure calculations. It reduces the strength of elastomers used in packers and BOBs and creates extreme environments for downhole electronics. Specialized muds with high temperature stabilizers, synthetic-based fluids, or even formate brines are used. Equipment is rated for the temperature environment and carefully selected. Drill string design must account for thermal expansion and contraction. Cementing becomes more complex as cement compositions must be engineered to set properly at high temperatures without degradation or strength retrogression. Drilling in HPHT environments requires enhanced well control equipment with higher pressure ratings, often 15,000 or 20,000 psi BOPs, more comprehensive monitoring systems, and highly trained personnel. Pressure while drilling sensors provide real-time formation pressure data, allowing early detection of overpressure zones before they cause kicks. Managed pressure drilling techniques, where surface back pressure is precisely controlled with automated chokes, allowing drilling with narrower margins and better control than conventional methods. The ninth problem area is directional control issues in deviated and horizontal wells. All wells have some deviation from vertical even when drilled with the intention of going straight down. Intentionally deviated wells require continuous monitoring and steering to follow the planned trajectory. Build rate, which is the rate at which inclination increases, and turn rate, which is the rate at which azimuth changes, must be controlled within narrow limits. Building angle too fast can create a dogleg, a sharp bend in the wellbore that causes high drag and torque, makes running casing difficult, and creates stress concentration points where the drill string or casing can fail due to fatigue. Reactive torque from the mob motor creates a tendency for the well to walk or drift in azimuth, typically to the right with a right-hand rotating bit. Geological factors such as dipping heart formations can cause the bit to drift up or down dip regardless of steering input. Maintaining directional control requires experienced directional drillers who interpret MWD data and adjust drilling parameters and tool face orientation continuously. In extended reach or complex trajectory wells, rotary steerable systems, which can steer the well while the entire drill string is rotating, provide better hole quality and faster drilling than motor sliding techniques. The 10th category is temperature-related problems beyond HPHT concerns. Permafrost zones in Arctic drilling create problems when the drilling mud melts the frozen formations, causing instability. Hydrate formation occurs when drilling in deep water where cold temperatures and high pressures cause water and gas to combine into ice-like solids that can plug the VOP or flow lines. Methanol or glycol must be used to prevent hydrate formation. Throughout all these problems, the key to successful drilling operations is prevention through proper planning, continuous monitoring of all parameters for early warning signs, immediate response when problems are detected, and maintaining well control at all times. Crews must be trained to recognize symptoms and take appropriate actions quickly. Advanced technology including real-time data monitoring, automated systems, and sophisticated modeling tools help predict and avoid problems, but human expertise and judgment remain essential. Every problem encountered provides learning opportunities that improve future operations. The drilling industry continuously develops new technologies, procedures, and best practices to make drilling safer, more efficient, and more reliable despite the inherent challenges of drilling miles beneath the surface in an environment that cannot be directly observed. When the well reaches the target depth, typically determined by LWD data showing that the planned reservoir interval has been penetrated, drilling stops and the comprehensive evaluation phase begins. The drill string is stripped out of the hole and wireline logging tools are run. Wireline logging uses an electric cable to lower instruments into the well. The cable, which may be 20,000 feet long, has conductors that provide power to the tools and transmit data to the surface. Multiple logging runs are made with different tool combinations. A typical logging suite includes several key measurements. The gamma ray log measures natural radioactivity from potassium, thorium, and uranium in the rock. Shales have high gamma ray readings, while clean sandstones and carbonates have low readings. The resistivity log measures how easily electric current flows through the formation. High resistivity indicates hydrocarbons in the pores, while low resistivity indicates conductive salt water. Multiple resistivity measurements at different depths of investigation help determine invaded zone properties versus virgin zone. The density log uses a radioactive source, typically cesium-137, that emits gamma rays into the formation. Detectors measure how many gamma rays are scattered back. Dense formations scatter more gamma rays. Porosity is calculated from the bulk density. The neutron log uses a radioactive source, typically americium beryllium, that emits neutrons. Hydrogen atoms in the formation slow down the neutrons. Detectors count the slowed neutrons. Since hydrogen is primarily in pore fluids, this measurement also indicates porosity. The sonic log measures how long it takes for sound waves to travel through the formation. Travel time is related to porosity and rock type. By combining these measurements, petrophysicists can calculate formation properties, including porosity, water saturation, and hydrocarbon saturation. The key equation is the Archie equation, which relates resistivity to porosity and water saturation. If porosity is 20% and water saturation is 30%, then hydrocarbon saturation is 70%. Multiplying hydrocarbon saturation by porosity and by formation thickness gives hydrocarbon pore volume per unit area. This is used to estimate reserves. Additional specialized logs may be run, including nuclear magnetic resonance, which measures pore size distribution and flow properties, and dielectric logs, which can distinguish oil from water in formations with very salty drilling mud. The logging data is analyzed in real time by logging engineer and petrophysicist.
They identify zones with good porosity, high resistivity, indicating hydrocarbons, and sufficient thickness to be commercially productive. These zones are candidates for completion. Completion is the process of equipping the well to produce hydrocarbons. The simplest completion will be to set production casing through the reservoir, perforate holes through the casing, and cement into the productive zone, and allow oil or gas to flow into the wellbore and up to the surface. More complex completions might include multiple producing zones, artificial lift systems, sand control equipment, or advanced technology like inflow control devices. Based on the logging results, the completion design is finalized. Production casing, typically 7 inches in diameter, is run through the entire production hole to bottom. This casing string is called the production liner. The casing is run with centralizers and accessories. A liner hanger may be used, which is a mechanical device that suspends the liner from the intermediate casing rather than running it all the way to the surface. The production casing is cemented in place. The cementing operation for the production interval is critical because the quality of the cement bond affects well performance and zonal isolation. If cement doesn't fulfill the standard requirement of isolation in the annulus or has channels, different zones can communicate behind the casing, and the well may produce water or gas from unintended zones. After cementing and waiting for the cement to cure, the well is prepared for perforation. Perforating is the process of creating flow paths from the reservoir into the wellbore by shooting holes through the casing, cement, and a short distance into the formation. A perforating gun is assembled at the surface. The gun is a thick-walled steel tube, typically 2 to 4 inches in diameter, containing shaped explosive charges. A shaped charge has a metal liner, often copper or tungsten, with a conical cavity. When the explosive detonates, the liner is formed into a high-velocity jet that can penetrate steel, cement, and rock. Each charge creates a perforation about 0.5 inches in diameter, extending 6 to 18 inches into the formation beyond the casing. The perforating gun is lowered into the well on wireline or tubing. Wireline conveyance is common for vertical wells. The gun is positioned at the desired depth using gamma ray correlation to ensure it is opposite to the correct productive zone. Tubing conveyance is used in deviated or horizontal wells where wireline may not reach bottom. The perforation plan specifies shot density, typically 4 to 12 shots per foot, and phasing, which is the angular spacing of shots. 0-degree phasing puts all shots in a single line. 180-degree phasing alternates shots on opposite sides, and 60-degree or 120-degree phasing distributes shots spirally around the casing. Phasing affects the stress distribution around the wellbore and can impact sand production. When the gun is in position, it is fired electrically. The explosive detonation is extremely fast, less than a millisecond, but creates a high-pressure shock wave that resonates in the wellbore. If the well is underbalanced, formation fluids will immediately begin flowing through the perforations into the wellbore, bringing with them rock fragments, cement debris, and drilling fluid that has invaded the formation. This initial flow cleans up the perforations and removes near wellbore damage. This practice is called underbalanced perforating, and it is better than overbalanced perforating when it comes to leaving less formation damage into the reservoir. After perforating, production tubing is run into the well. Production tubing is a smaller diameter pipe, typically 2 3/8 to 3.5 inches, that provides a passage for produced fluids to flow from the perforations to the surface. Running tubing instead of producing up the larger production casing has several advantages. The smaller diameter increases flow velocity, which helps lift liquids to the surface. The tubing can be removed and replaced without pulling the casing. The annular space between tubing and casing can be monitored for leaks. Downhole equipment can be set in the tubing and retrieved. The tubing string is assembled joint by joint as it is run into the well. A packer is set at the bottom of the tubing string above the perforations. The packer is a sealing device that isolates the tubing casing annulus from the producing interval. It has rubber elements that expand to seal against the casing wall when the packer is set, typically by weight or hydraulic pressure. Perforations can also be done after running production tubing either with or without the rig on site. At the surface, a Christmas tree is installed on the top of the wellhead. The Christmas tree is an assembly of valves and fittings that control flow from the well. It typically has a master valve that can shut in the well completely, a wing valve on the horizontal flow line for production, another wing valve on the horizontal flow line for killing and injection, and a swap valve for running wireline tools and various pressure gauges and fittings. The tree is rated for the maximum expected wellhead pressure, commonly 2000, 5000, or 10,000 psi. All valves can be operated manually and often have hydraulic or pneumatic actuators for remote operation. Safety valves may be included that will automatically shut in the well if pressure drops suddenly, indicating a line rupture or if fire is detected. With the tubing and Christmas tree installed, the well is ready to be flowed for the first time. Initial flow testing establishes the well's production characteristics. The well may flow naturally if reservoir pressure is high enough to overcome the weight of the fluid column in the tubing and the pressure in the flow line. For our 12,000-foot well with typical reservoir pressure at the depth, natural flow is likely, at least initially. The well is opened gradually by slowly opening the wing valve. Fluid begins flowing from the well. Initially, the fluid is mostly drilling fluid, completion fluids, and water that enter the formation during drilling. This is called load fluid. As flow continues, the proportion of hydrocarbons increases. For an oil well, the flow becomes mostly oil with some associated gas and water. For a gas well, the flow is primarily natural gas with some condensate liquids and water. The flowing fluids are directed through a test separator, which separates gas from liquid. Flow mirrors measure the gas rate in thousands of standard cubic feet per day, or millions of standard cubic feet per day, and the oil rate in barrels per day. Water production is also measured. The fluids are sampled for laboratory analysis. Oil samples are tested to determine API gravity, sulfur content, viscosity, and other properties that affect value and refining requirements. Gas samples are analyzed for composition, including percentages of methane, ethane, propane, butanes, carbon dioxide, hydrogen sulfide, and nitrogen. The presence of hydrogen sulfide, which is toxic and corrosive, requires special materials and safety procedures. The well is flowed at several different rates to characterize its productivity. A well test might flow the well at a high rate for several hours, then reduce the rate, then shut in the well and measure pressure buildup. The pressure data is analyzed using well test interpretation techniques to determine the permeability of the formation, the skin factor indicating near wellbore damage or stimulation, and the drainage area of the well. This information is critical for reservoir engineering and predicting future production. If the well has lower productivity than expected due to formation damage, stimulation treatments may be performed. Stimulation treatments are designed to improve well productivity. For sandstone reservoirs, acidizing may be used. Mud acid or hydrofluoric acid is pumped into the formation to dissolve clays, carbonates, and other materials that reduce permeability near the wellbore. For carbonate reservoirs like limestone or dolomite, hydrochloric acid creates channels and enlarges pores, significantly increasing permeability. Hydraulic fracturing is used in low permeability reservoirs. Fluid is pumped into the formation at pressures high enough to fracture the rock. Proppant, typically sand or ceramic beads, is carried into the fracture by the fluid. When pumping stops, the fracture tries to close, but the proppant holds it open, creating a high permeability pathway for hydrocarbons to flow to the wellbore. Fracture treatments can extend hundreds of feet from the wellbore and dramatically increase production, especially in shale or tight sand formations. Once the well is producing at satisfactory rates, it is connected to permanent production facilities. In remote locations, this might involve building flow lines to a central gathering station miles away. At the gathering station, fluids from multiple wells are combined and processed. Oil is separated from gas and water, then stored in tanks before being loaded onto trucks or pipelines. Gas is processed to remove water vapor, carbon dioxide, hydrogen sulfide, and heavy hydrocarbons, then compressed and sent to sales pipelines. Water is treated and either re-injected into disposal wells or recycled for use in drilling and completion operations. The drilling rig is moved off the well once the Christmas tree is installed and the well is flowing. Rig demobilization reverses the assembly process. Components are disconnected, lowered, and loaded onto trucks. The site is restored to the extent required by regulations, with the wellhead and access road remaining. The rig moves to the next location to drill another well. For the rig crew, the process repeats, with each well presenting unique challenges based on the geology, depth, and objectives. Over the life of the well, production rates will decline as reservoir pressure depletes. Initially, the well may produce 500 to 2,000 barrels of oil per day,
but this rate typically declines exponentially, dropping 20 to 40% in the first year and continuing to decline more slowly in subsequent years. Eventually, reservoir pressure becomes too low for natural flow, and artificial lift must be installed. The most common artificial lift method is a rod pump, commonly called a sucker rod. A surface motor drives a beam that moves up and down, operating a downhole reciprocating pump that lifts fluid to the surface. You can check our channel where you will find a detailed video on the operation of sucker rods. Other lift methods include electric submersible pumps, which are multi-stage centrifugal pumps run on electricity conducted down the well, and gas lift, where compressed gas is injected into the tubing to reduce the density of the float column and allow reservoir pressure to lift it to the surface. The well will continue producing for years or decades. Economic life depends on production rates, operating costs, and hydrocarbon prices. When production drops below the level needed to cover operating costs, the well is plugged and abandoned. Plugging involves filling sections of the wellbore with cement to permanently seal it and prevent any flow migration between formations or to the surface. Regulatory agencies specify detailed plugging procedures to protect groundwater and surface environment. The wellhead is cut off below ground level and the site is reclaimed. This completes the full life cycle of the well from initial drilling to final abandonment. This comprehensive process demonstrates the complexity and scale of modern well drilling operations. It combines advanced technology, skilled personnel, careful planning, and continuous monitoring to safely access energy resources miles beneath the Earth's surface. Every well is unique, requiring adaptation to specific geological conditions, but the fundamental principles and procedures remain consistent across the industry.